Swayam Prabha. Digital India. Educated India.
So, welcome again everybody, day 2. Even I am settling in slowly to the routine and time adjustment, how much to prepare for 3 hours and all that, it will get better. So, today again it is a lot of introduction to actual blast parameters, a lot of basics, terminologies again in more detail, getting introduced to numbers. For me, as I had mentioned, keeping those numbers in mind, that is the only way I know if I do a simulation or something like that, I get some answers, and simulation is only as good as the parameters you put in and the models you build. So, to be realistic, so to speak, that is why I put a lot of importance to some of these, although it might seem very basic. So, we will go through that. So, but before that I wanted to address there were 2 people actually, I think Pratibha was one and there was another person who asked a question. So, what do you do with the chart, with the values that you calculate with risk level? So, I was asking you yesterday during the tutorial for the design basis threat. So, that is, and we will look at it some more. So, that is a real quantity that we use for design. But then the planning risk level, if you see, you calculate, and this is, if you see, there are some chart, there is a chart out here. So, this gives you the design basis threat and then the level of protection. Then you calculate, in this case the level, risk level was 0.2. So, most of you were asking, I got less than 0.1 and someone said 0.17. So, if it is, then you go to the standoff distances and you see how costs, there are more to it. These numbers do not just come by magic, there is calculations beyond why even the decimal is there. So, and I do not know myself. So, that depends again the organization and how you build up from a standoff distance to a cost increase. So, this way you can plan land usage, how much land you have, that is always restricted. And then you can create a chart like this that says, okay, if I do not have this much land, this is what it is going to cost with this risk level to go from unprotected structures for intentional threats. So, that is how it is utilized. But again, that is not going to be the focus, this part is not going to be the focus of what we do. So, so we talked of, so yesterday was, and I like to write, as I was saying, so you can take down most of these notes. These notes will also be available to you later on. I do not know if the size, let me know, we will work that, that is size 8. It's going to be size 7, and let's see if this works better. So, yesterday what we saw was, one was risk assessment. We spent quite a bit of time looking at the risk assessment aspects of it. And then the second thing I'd like to do is blast standards. And I'd like you to be exposed to one of the blast standards, which is ASCE 59. There is 11, and also I believe it has come now. I do not have a copy of it, maybe the update ASCE 59 22. And I did bring a copy of it just to show. So, this is blast protection of buildings. This is a document in both units, and this is from the American Society of Civil Engineers. And if you see in this case, maybe I can, so you will see that this does not give you design guides, although it in the US there are several types of documents. One is a code which is legal. This is what is known as a standard. Like you have a material standard, you know, steel, it is some standard that is held everywhere. Same thing, this is loading, not a loading standard, but a standard for protection of buildings. So if you see here, the chapters are, it covers everything. It has got design considerations, it's again not details, design considerations, it's got performance criteria, then it's got something on loading, then fragmentation, structural systems protection, material detailing and performance qualification. And it does talk of risk assessment, as if you see, that's the very first chapter again after the introduction. There is they also have, we are actually considering, it's been in discussions for a while, but we haven't yet come to a consensus or methodology of getting a certificate program in the US through our ACI 370. It takes a lot of motivation to see why it is needed, and maybe a course like this, engineers who are working can do it and then get certified as a specialist in that area. So those are those qualifications, that's part of the qualifications you look at. And so same thing that we discussed yesterday, all 4 components, how you do it is different. There is, for example, FEMA, they have their own way of risk assessment, but we've done 2 different methodologies, and that is plenty where the risk planning, the risk numbers that you calculated, then you see how to reduce each one of them. If you want to bring that risk level from 0.2 to 0.1, then the consequence, threat and vulnerability reduction is a big aspect of it. How can I change anything to reduce those numbers? So that's the strategy that you should adopt if you are using the risk analysis procedures, apart from coming up with a design basis threat. So our job as an engineer is not to just come up with a loading, but also to reanalyze and say, okay, I do this, and then these are, because these are big money changes, if you can spend a little time here. Then they are, the levels of protection is here. Again, we talked about these levels of protection from very low, medium to high. And again, the damage we will discuss later on in terms of what are known as, where this comes into play is pressure impulse diagrams. So we'll talk about the structural damage as related to levels of protection. And so here they are, then talks about glazings, levels of protection, then response limits. We'll also be going through some of them. I'm not going to take material from this document directly. I haven't taken a permission yet to do that, or I don't even have an electronic copy, so I haven't purchased it. So I'm not going to do from that, but we have other sources. So we'll talk of all these things. We'll talk of strength increase factors, we'll talk of dynamic increase factors, reduction factors, we'll be talking of remaining strengths, we'll be talking of some of the design requirements, analytical procedures, all these are addressed. Modeling, we'll do single element response, structural systems. We are doing finite element a little bit. You'll have a demonstration, and also I think we are developing a lab for you to use Abacus, and that's really cool. Then modeling of elements, we'll talk about that, but things we don't talk a whole lot is in terms of connections and joints. That's more in detailing. Then we will look at these tributary loads, load combinations, and some of the clearing effects. These are more in clearing effects, is especially in confined explosions. I'm not spending a whole lot of time in confined explosions because confined explosions is very complex. Even unconfined explosions, there are 2 different varieties, and you can spend problems doing in both, and the numbers are different. So I will try to present one example on a confined explosion. Confined explosion depends on the room, openings, sizes, so many different aspects of it. And it talks of different structural systems, and this course will have a few of these. I do plan to put some precast in there so that you can see. Then the response characteristics, definitely today and tomorrow, not today, hopefully by today I'll start introducing, by tomorrow we'll start looking at response characteristics. Then the standard talks about these are more internal threats, safe havens. I don't think I'll get into some of these so much. The design intent, of course, will be including some of this. Fenestration windows, I have a little bit of it. So the standard talks about what is there, what type of analysis to use. There is a lot of testing that goes on. Most of the window systems, the way it works, at least in the US, is people manufacture the windows and send it for testing purposes and report. So instead of having a standard, the manufacturer have their own testing data that you can use to, and then of course they sell it based on that. It happens even with a lot of other types of structural systems there. And doors we are not going to look at. So you see, it's very comprehensive. Talks of non-load bearing external walls. So yesterday we discussed how to, I mean, that can be a big hazard, and that has been addressed here. I'll see if possible I will bring some aspects of it later on. Roof systems, we'll look at one roof system. I think I have an example on one roof system. It's not a composite construction, but it can be applied, similar principles can be applied there. The retrofits, I don't think I'm going to spend time on it, but as you can see, there's so many varieties of retrofits. Security films, window films, blast curtains. So basically behind a window you have a curtain to collect, but again that reduces or that eliminates the whole purpose of having a window. But in critical places where it is needed, there is an opportunity to do that. Catch bar systems, again this is behind the windows so that the windows don't blow out in. Fabrics, FRPs, and there is a bunch of research also going on in these areas. Amplification, the addresses amplification and reduction of blast loads based on the shape and size. Yesterday we also talked about this, so the standard addresses that. And then there is materials detailing. We will definitely get into some of these things. The reference documents, just for your information, ACI 318 is our concrete code, and then ASTM 615, that's the steel, it's basically the rebars, and same thing, these are all rebars details. And further along it talks of interaction between the primary and the secondary elements and how to detail them. It's got chapter 21 on codes on concrete, steel and composites, masonries, fiber reinforced composites. So as you see, this gives, and if I open this up, you'll see there's not a whole lot of, there are some equations of course, but not a whole lot of equations. There are here, we will look at some of these. So it's more about a specific what limits and things like that. So I'm just running through. So if you're interested, these are some nice documents. This is old, as I say, I do have a copy of this. Originally many of these things started from petrochemical blasts. So that it's an older document, they are trying to update it. I know the committee has been working, I keep hearing about it, but they haven't. But it still is a good reference if you want to if you work in the petrochemical industry and you're designing. And this is also physical security, so from petrochemical and building. So those are the two documents. And then the AISC, it has blast and progressive collapse. Similarly, the PCI has, ACI is the one I talked about, we have. So that's a little bit about the ASCE 5911. So, we'll start with so we looked at the risk assessment parts of it yesterday, and so now we'll look at, and some of you did ask me this question, what about if I calculate a DBT, I mean I could put anything out there. Well, that is the term for uncertainty. So there is a lot of uncertainties and assumptions. So even amidst this chaos, you still have to define some things for clarity purposes. And so that's what the idea today is. We will go through. So the lot of things in terms of uncertainties and assumptions. What are all the different uncertainties? The first one is, as we talked yesterday, the threat parameters. Oh, thank you. And the threat parameters, this comes in terms of the design basis threat of the threat, namely W and R. So this is kg and meters are the standard units. I'll try to look at both the units as we go along in this course. And so this is the location, and if you see, the location is still prescriptive. So the size of explosive and this is the location R, both are still prescriptive. And that's why if you are able to build models, then you can change those, but those complicated models really take a lot of understanding of how advanced finite element programs work, and they are very rarely used. There are companies, I should say, that have their own specialized software that do nothing but this. So like Gagosian case, there are other companies also that just do nothing but, and they do advanced analysis, so to be less prescriptive. Then the second one is the blast loading. This is also an uncertainty. So in blast loading, you have one, air blast effects, and the second one, there are other effects also, ground effects. This and things that were not covered is ground effects such as cratering, fragmentation. All these are part of uncertainties that are there in blast loading. And then the third one is element modeling. So once you have an idea of, or you have nailed down something that you want to proceed with, then comes how do I take a real structure and come into element modeling. And in element modeling, a variety of principles to understand is structural behavior, or structural behavior and structural modeling. So here it comes in terms of analysis methods, and whether you want to use the single degree of freedom systems or you want to use multi degree of freedom systems based on finite element methods. There are other methods also, really cool methods called smooth particle hydrodynamics, that's not quite based on finite elements. Principles are there, but it's not, you're not modeling a structure. You can actually see nice explosions, and it is used for especially in for example, there is a ground blast, and you have an armored vehicle going, modeling of some of those. And we are working with some of the latest modeling softwares that are actually classified and given on the basis of what is needed. So there are a lot of advances, but again this is very, very specialized. Some of these softwares can be really, really expensive also. So the other next one, but we will focus on single degree and a little bit on multi-degree freedom of systems also. Then you have element material properties. And material properties are different whether you have for concrete, steel and masonry, and we'll look at some of them today. And once you have all of this nailed down, the fourth thing that comes in is the element response. So you have a loading, and once you have decided on what the type of model it should be, you apply the loading, you get the response. And what are all the parameters that you include in your response? For example, whether you are looking at the force, you still have to come to the basics of design. So force, how do you convert what you get? Even if you do single degree of freedom systems, you are not going to get the force and moment in some of the programs unless you write a code in MATLAB or whatever to convert everything. You're still not going to get directly, but how do you take the parameters you get and convert it into something that you can design? This also comes in terms of what are known as resistance functions. It's an important concept that is a part of blast design. Resistance functions can be analytical. Of course, analytical is, this is the advantages is it is general, but it is there's a lot of limitations, but this is the best you have and it is accepted to use. So you can actually calculate a response and say this is what it is going to be, or you can do experiments. So you take, for example, a slab and don't want to move that. Okay, no idea. Okay, so you take a slab and let's say you're constraining it here and here, and you're applying a load, and you know the pressure versus time on the load, and then you get P or F, the force versus time, and then you'll get a function something like this, a response like that. So there's a lot of, it's expensive, you don't know how accurate your measurements are, especially certain materials, and then it is limited to the boundary conditions of that particular experiment that you do. But again, it's very commonly done. It's maybe at this point I can mention, it's not necessary that everything is done using an explosive. So there are, I think Professor Agappan is going to show you some shock tubes. So that's one way to do it, simulate without an explosion itself. There are other ways using water pressures, and there are lab facilities that will create, simulate this type of loading. Although to create this type of strain rate, that could be a challenge. So there are a number of ways you can do experiments. People have designed what are known as what trees? They are called loading trees. Loading trees in order to come up with doing experiments here. So and then the second thing is your deflection response, because the deflection response is directly related to LOP checks, and also from the LOP checks you get the limits. So, those are some of the things we will cover today. So, let us start with threat parameters. The first one, so some of the characteristics are, as I talked about, it is prescriptive, and as I said, these are the minimum standards, whether you are using a DoD or some other. Then minimum standards, this is for DoD, and for TSA, for example, your security agencies, they can have their own. For them, what is important is the vehicle type, size, that is more important to keep them away from any entrances and things like that. And then you use risk analysis for DoD, for FEMA or other such agencies. So, in this we have seen that the threat is specified in terms of TNT equivalence, or I can say TNT equivalence. So, let me import yeah. So, I hope you will be able to see it. If not, I think when you print it out, you should. Is that clear or not? Not quite. Okay, I will try to read it out. So, if you see, there are charts like this. This is basically the explosive. Types of explosives. As you see, there are so many different types of explosives. Some of the more common, composition B or explosive D. This is the one we talked about. This is ANFO, and it gives you the density, and then the equivalent mass. If you see, there are two different equivalencies. Some documents do have single equivalencies, but then you have an equivalency based on two metrics. One is pressure equivalence. So, how much of a certain explosive do I need compared to 1 unit of TNT to give the same pressure? But then you also, it does not mean you will get the same impulse, because the positive time of loading could be different, positive phase. So, impulse equivalence, and these numbers are not the same. For example, if I go ANFO, so this number you see for pressure equivalence is, in this case it is the same, 0.87, and this is also 0.872. But there are other cases, for example, if you see, this is 1.14, so this is 1.14 and this is 0.97, and the pressure ranges are also given. So, this is the pressure range in megapascals. So, that is one of this is a chart that is utilized, and let me give you another one in relation to that. So, I think this is the ASCE 5911. I can look into that, look up that. I'll keep that question and I'll let you know. I believe this is from ASCE 5911, but don't quote me on that yet. This could also be, so now sometimes I also wonder, these same charts are there in multiple books. So if I go to ACI some books, you'll find the same charts. So I haven't paid enough attention to see what is the original source of it. So I don't know where I took this from, and I don't quite remember what the original source is. So there are two things associated with it, but I'll find out and let you know. So here if you see the TNT part of it, this is, so that's right, the basis out here. So this is TNT, and so the density, if you see, this is 1630 megagrams. It's good to know these numbers. So the density of TNT is 1.63 megagrams per meter cubed, or 1630 kilograms, right? Am I right? Per meter cube. So so that is, and then both equivalencies are 1. So another commonly considered one is PETN. So like that there are so many different varieties, and this is where you would go. The pressure ranges is also important. If you give, for instance, say something equivalent to 1, so this is 1 out here. If I go something close to 1, or let's say here, so this is octal, so this is also close to 1, and the pressure ranges, it doesn't say standard, but here it gives you what are the pressure ranges that it is basically. What standoff distance you mean? Oh, here once you have the standoff distance, we'll go through how to calculate those pressures. So once you have those two, then we forget about those two, and then we worry about just the pressure part of it.
Equivalence pressure is calculated based on both.
Not sure I follow the question. So let me try to explain it again. So you have two different explosives. So you have a certain standoff distance, and then we'll talk of the scaled part of it later. Maybe hold that question, see if that. So you can take the standoff distance out of the equation based on a scaled parameter. So for example, if you are designing for PETN and the factor is 1.23, mostly they use equivalent mass for pressure. So the pressure one is used more commonly. So if you have, let's say, 100 kilograms of TNT, your design is going to be here. If I bring that, it is 1.23, I think. So the design PETN is 1.23 times. So you'll go with 123 kilograms of, so those are the charts out here. Then things to, what are the sizes of explosives, and I'll going back and forth between the two units, so bear with me on that, but you can do the conversions. So again, this is based on the UFC 420 this -01. So we've seen several things. If it is very low DBT, then you are looking at 55 pounds. So 55 pounds is about what, 20 kilos, 20 odd kilos of that, right? 25 kilos maybe. So 55 pounds, and in a 4,000 basic car, it's about 2,000, 3,000 pounds. Then if you are looking at a low DBT, then you are looking at designing for 220 pounds in again the same type of vehicle. Then we come to medium DBTs, and this jumps up next to, there is nothing that prevents you from using in between numbers, but if you want to design, that's the difference between a code and a standard. These numbers are not quite standard. These are all guidelines. If it is a standard, you can use them directly, and legally you're, not legally I should say, you're protected in some ways, the book protects you. Otherwise it's your call that you have to justify. Then in the high DBTs, then you are now looking at 1100 pounds. And now for this you need a bigger vehicle, maybe a truck. And you also have very high DBTs going up to 4,400 pounds in a 15,000 pound truck. And then you have very special, this was the Kobar towers of 20. So this is not unreasonable, these numbers, or these are not impractical numbers that you are designing for. So then you look at prevention methods. I don't know, for some reason I have come to IIT quite often, but every time I come in now I see security 1, security 2 and all the spaces, and my mind is thinking standoff distances and all kinds of stuff instead of enjoying the nature there. But anyway, so prevention methods, it's a really secure place in many ways. It's easily securable also. A place like this is, if you want to increase the level of security for anybody here, this is one of the best places within the city. So a placed bomb, for a placed bomb you're looking at several ways to, you can have trash containers eliminating wherever they are. That's an easy way to, small things that you can do. You can have, for example, what are known as bollards, or barriers, several barriers. Bollards are nothing, you know bollards, right? You just put some solid cylindrical material around to protect. So those are, or other types of concrete barriers. So you can use that as prevention. Then if you look at the destruction caused by explosives, and let's look at a few nice examples, especially if you work in research and or even otherwise. This is again from the UFC 340. We will go into all that over the next few days. So what you see here is the UFC, this is from UFC 340. So what you see is the survival of lung, this is for lung damage, and I'll show you for other WH. So this is in terms of scaled impulse. I know I haven't quite introduced that term. So this is scaled impulse in terms of impulse divided by the weight, and this is the overpressure. We've talked of the overpressure already. Going from 10, this is in PSI. So remember, 1 PSI is 1 kilopascal, or 1 KSI is 1. These are the terms if we use So keep these two numbers in mind for quick conversions. So 10 psi all the way to 1000 psi, but most of the ranges, this is itself very high. Once you start getting into a 100 psi range, this itself is very high. So the 1%, this is the threshold curves, as you see, as the impulse keeps increasing. This is an increasing impulse. This is 1% survival. So there are curves like this that can estimate where the survival rates are. And this is actually a very nice table that I have found and I have used, especially to check some of the results I get. If I do a simulation and I come and I have to find, okay, does it make sense? So this table, it's a very nice table. And it gives us, for again, this is from the same UFC. So if you look here, for eardrum rupture, that's the first. I don't know if you can you read that, or do I need to write it? Make it a little bigger. Yeah, if I make it bigger, I sometimes worry about now I think once I pasted it, I can't. Sorry. I just realized. I don't know I think then it becomes part of the image. It's not able to. But okay, I'll write that. So this is eardrum. So let's look at some numbers. Threshold, this is the in man, in humans, for air blast of short durations. So notice this is 3 to 5 milliseconds. Pressures can also last up to 20, 30, 40 milliseconds. That's where the impulse comes in. If the pressures, even if it is exponentially decaying, but you apply it over 20 milliseconds, then these tables are not valid. So which means this is more for maybe hand grenade type, or somebody is soldier who's there, where they. So pay attention to what I'm trying to say here is pay attention to the time of the explosive, the pressures also. So that is an important consideration. So given that 5 psi is the threshold, and for 50% this is 5 psi or 5 kilopascals. That's no, I'm sorry, this is 7 kilo. Nobody corrected me. 7, yeah. Are you awake? So 5, so this is 35 kilopascals. I don't know how I put that equivalent. Then lung damage, if you see, so this is for lung, and it goes a little higher, which means you see that the human body is actually capable of withstanding a fairly high pressure for a short duration, of course. So this is 30 to 40 psi, and lethality, this is lethal force threshold is, that's a really high pressure. When you start looking at 100 psi to generate that kind of pressures with explosives, it takes a lot. It depends on the standoff distance. So most of these 3 to 5 milliseconds will be smaller sized explosives, maybe a kilogram or less, or 1.1 to 2 kilograms at say 1-2 meters or whatever it is. It's not that high. So you're looking at that type of numbers out here. Any questions? Anyway. Yes, somewhere in that range. Yeah. So yeah. Yeah. Yeah, these numbers won't be valid. And I don't know if you could research, so where if I were encountering a situation like that, I'll see if anybody has done more research on these to find out for greater. That's what guides me into looking at something else. Then we look at, this is another, more from a structural perspective. This is a very nice, this is a femur 350 so let me move it to the next page. So this is actually, I really like this chart. Here if you see, and you were asking about standoff distances, so here you have the standoff distances, and then you have here the weapon yield in pounds of TNT. So it starts with glass and minor cuts. Clearly you need much more standoff distances, even 10,000. So this is 10,000 pounds. We've talked of up to 20,000 pounds. Remember that. This is the highest range, and down in the 50s. So this is what 10 maybe in the, this is 20 pounds. No, 30 pounds. So 30 to 2000 range. Glass, minor cuts, severe wounds, glass with fragmentation, retention film, severe wounds, threshold injuries in open buildings, that is here. Between these two, potentially lethal injuries. So if you have, let's say, a 100-pound bomb at 100 feet. So what are we looking at? We are looking at somewhere in that range, potentially lethal injuries. So we are not looking here in terms of the pressure. The previous one was looking, the table was in terms of pressure. Now we are starting to design buildings. So this gives you a good idea for what columns can fail. So this is the one right here. So for the same thing, for a column to fail, you must be at about, let's say, 18 feet for 100 pounds. So let's say in this case a concrete, something to take away from this graph. There's so much to absorb, but one thing if you were to keep in mind, can concrete column failure, let's say 100 pounds at about 20 feet can fail columns, concrete columns. I mean, data like this is out there, and unfortunately people who planned the Oklahoma bomb, that was by somebody, a local domestic terrorist there, or whatever grudge they had. It was a same thing they did. Take one of the fuels out, one of the explosives out here and place it next to a column, or find the distance from a column, and so it gives estimates on what it can do, although you do not know the exact damage it can do. So you can look at that to get other ideas. Now the second uncertainty we looked at, do you remember what it was? You can cheat, you can go back and see. Blast loading. There's so much, there's really a lot to know about this. Funny thing is, a lot of it has been developed maybe in the some of it as late as late 1800s to early 1900s to mid 1900s, and then those are still being used. So I'll try to present some equations just to, and also we'll do some things in the workshop, may not be today but tomorrow, so that you get a feel for how these, why these equations look the way they do, and how to generate it if you were not using some kind of advanced finite element program or some other even advanced programs, how to calculate some of the pressures, although the charts, we'll talk about that also. There are So, the blast loading is, let me start with this one. It's going to take a lot to cover all of them, but we've talked a little bit about it to know the variety of characters, loading categories. So, these are the different blast loading categories. One is unconfined explosion, and the next is confined explosion. This is really extensive. As I said, openings, and the UFC does a really good job on covering whatever you want along these lines. But in this course, we will look at free air burst. Oh, there's a way to get that back. So, we'll look at free air burst, and then air burst and surface burst. So, a free air burst is more, say you have a building, and let me see if I can give a, so something like this is a surface burst, and a free air burst will be, I know you cannot hang an explosive, this would be a free air burst. And air burst is, so the surface burst clearly is you're going to have, as we discussed yesterday, reflections as well as, and then the max stem. Somebody asked a question yesterday, and I've got a nice graph for that. So, ask questions. The more you ask, I can get more information out and present it. I was telling Professor Argappan that I've started changing, we've shared a lot of the information as to what is to be presented on a day 1 to day 10 basis, but already changes are taking place. That comes only if you ask some of your questions. So, the pressure loads, if you see in all these cases, you have reflected, unreflected. So, if you have a free air burst, there is no reflected pressures, right. So, that is what you see out here. Air burst and surface burst, this is on the structure itself. So, you have the reflected protective structure is a shelter. So, this is your shelter. And then you have confined explosions. If you see confined explosions, there are a variety of categories of confined explosions. So, you have fully vented, partially confined and fully confined. So, fully vented is you are going to have openings here. So, these are the vents, and partially confined is if you have a structure like this is partial confinement, and fully confined is a structure like this. So, for each one of them the procedure is the same, it is just you have a different set of curves to bring your data from, but awareness, knowing that this is available, that is one of the goals of this course as well, is to sort of shine light on what is out there. So, I think this may be, I do not know if I have it right here. So, somebody was asking me this question, I thought I will present this. Yeah. So, this may be a good time to show that. So, if you see this chart, you were asking what is the height of the triple point, right? Yesterday, one of you asked that question. Now, what is a triple point? reflected wave and an incident wave coincide. So height from the ground to that is the triple point. So here if you, oh that's okay. So this is the scaled height. So we'll talk of what scaling is. Maybe I'm a little ahead, but that's okay. We'll introduce you to the term. So this is the scaled height. This is, if you see, so you have your building and your explosive is here, and then these are your incident, and then this is going to reflect out, and then your reflected curves are like this. And if you see the you connect all of these, so this is the triple point, all these are the triple points. So this is the scaled height ht, and here this is presented in terms of ht divided by w charge. Well, and these are the I think this is the z value, I don't quite have it, but there is a curve. So number indicates the scaled charge height. This is the scaled charge height. So this is in terms, I'll have to see what was there, but there is this figure 2.13 you can look up. This is in UFC 340. And one thing we talked about was to design against it. Won't get into that detail so much, but I thought I'll get this to answer one of the questions, how to calculate the scaled height. But what is of importance is you are given the W and the R values. Basically you are given the load value, and you are also given the standoff distance. From here we get a pressure time curve. So we go till sorry, 9:30, 11 o'clock, right? Okay, another half an hour, that's fine. So we'll spend some time on this. I'll present equations, but I'll start with an introduction to it. Now when you have an explosion, and there are different types of explosions, and this is your, I think this is going across pages. So this is your R and W, and you have at this point pressures acting on it. So typically it converts to a form that looks like this. This is P, and there are both incident, and this is P as a function of time, and this is the time itself. So there is an atmospheric pressure P naught that is acting. P naught, anybody knows the value of how many bars? 0.01 bars, right? What's that?
1 bar.
Yeah, 1 bar. One bar is fine. Yeah, 1 bar is what, 0.1 megapascals? 0.1 megapascals. So atmospheric pressure, it's good to know P naught is atmospheric pressure equal to 1 bar is 0.1 megapascals. So, and then from here it does take a little time to come. So this is what is known as the arrival time. So you have here from wherever you are, there are lots of theories and equations to calculate that, and then there is a jump. So, and the jump often, it depends on the type of explosion. So you have here, this is the rise time. As we see, these are very quick, perhaps even less than milliseconds, the rise times those numbers. And then the peak pressure, and then you have the curve actually will sort of exponentially decay. And I'll want to show you, I've not done in some other classes, but here I'd like to, because it's good to see how complex this whole phenomenon is. We are talking of uncertainties, right? And some of the equations you'd see seem so certain of those numbers. There's sort of a little irony out there. When you see it, I'll present it and show it to you again. So this is an exponential decay. So it rises to the peak, let's say this is your PSO, and the area under the curve here. So this is the positive phase. This is your positive duration up to this point. So let's call this TD, duration of time, positive. And this area is the positive impulse. And this area here is the peak. So this is PSO plus, let's say. This is PSO minus, two different variables. And then you have the negative phase duration. This is not very important, but it is the duration is not as important because the pressures are much lower, but it is important to consider the negative phases under certain design considerations, because it causes suction, and people forget that, and that can result in designs that could be not safe. So this is the negative phase, and this is the negative impulse. Impulse is nothing but pressure time area under the pressure time curve, right? What's that? The positive duration is considered to be from the peak to down. Usually the rise time is probably a tenth or a hundredth of the positive duration. Rise times comes into play when your pressures are low, and even there then the pressures, you don't consider it as a rise time, because then it's more of the deflagration situations. Most explosives, at least, I mean, I've not seen where a rise time affects results so much. Yeah. So it's even an order of a thousandth of a millisecond, right? Yeah, you're right. Now this is idealized, of course. Reality is you'll have, if you see, you're going to have maybe, this is going to be the way, if you measure, it might be anything like this. It could go, so whatever, and we've got a lot of data on this. We've done experiments. This was many years ago. So this will be how the reality, of course, capturing this curve from the data, of course, presents a lot of challenges, right? Reduction of noises, elimination of that, and then trying to fit a curve. All those interested in PhD, that's where you're spending some of your time on, is to clean the curves, the data that you get. And that's the case with any data set. You're going to have a lot of noise, and how to separate noise, and that's one of the challenges I faced often is, even in images, you take images, what is noise and what is reality, right? It can be very hard to, you're making a judgment on your own. Question becomes, is your judgment clouding the information, the actual information. Now, of course, something like this we will look at it in greater detail, but for design purposes, something like that, even that is not very convenient. So, for design purposes, we look at data that is little more linear in nature. So, if we take the structure is subjected to positive the atmospheric pressure anyway. So, that if we discount it, then what you are looking at is, let us say this is P versus T, you are basically looking at linearizing the positive phase. So, this is linearized positive phase, and the negative phase is also linearized, if I can say that right, in this manner. And so, this would be your TD, and you have in the negative phase two different variables to account for, two linear variations. And so, this way now your, if this is P naught and TD, your impulse positive is going to be 1/2 P naught TD. Same thing with the negative side, you can calculate. So, that TD, the way it is calculated, so TD is this is TD plus, this is different from, this is 2I plus divided by P naught. These two P naughts are the same. So, this value peak, we maintain the same peak value. So, the same peak pressure, but your load duration TD adjusted is from your impulse equivalence. So, that is artificial in nature, and you have impulse equivalence there. So, afternoon session you are going to see a demo of that. I work in creating numerical shock tubes, so to speak, simulated shock tube. We have access, but they are pretty expensive. I do not have one in our lab. I know there are one university that does have a shock tube, they do. But the problem becomes there is, I mean, how do you keep feeding that, right? It is a huge investment, and you have to keep feeding that large elephant.
This graph is we are making this straight line because the TD is very small. So my question is, what would be the maximum value of TD for which we can say that we cannot do this kind of approximation?
I do not know if I have a number value for you. Yeah, so yeah, it depends on the peak pressure too, right? If your peak pressure is low, then if your peak pressure is low and the TD is very high, then the decay is not going to be. We will talk about some decay equations. There are a bunch of theories. I've got a segment on decay equations and also a tutorial that you can work on. So this is another thing we talked about was, we said the difference between the incident pressure. Now, incident, the word side on, all these are used PSO, all these are used PI, PSO or capital PI capital PSO, all these are used in the same context. They are the same thing. So don't think of them as separate. And then you have on a structure, you have reflected pressure. Reflected pressure is going to be PR. So we've seen yesterday that just before it strikes, and of course it's not going to be uniform, this is your PSO, and then it reflects off on the structure as soon as it hits on the structure itself. This is PR. The stiffness of the structure is not quite considered, although in bio testing, if you're testing specimens related to the bio applications, that could come into play. These equations will not be valid there directly because structures, body can move. So we are talking of more of rigid structures. So the same thing, if you see, you have the, let's say this is your PSO curve. The reflected pressure also tends to, so your reflected pressure is going to be much higher, and it tends to follows, so it tends to go again, I am not drawing it very well, but thing to keep in mind is it follows a similar pattern, but the reflected pressure value is much higher. And to give you an idea, so let me bring this, all these curves again are from UFC 340. So if you see here, the peak incident pressure, this is PI or PSO. So here you have, this is PSO and this is PR versus PSO, and it depends on the incident pressure. So values up to, I said about 100 psi is typical, max, so somewhere in that range, at least in this course we'll be talking about, nothing more than that. And so you can see the reflection coefficients going all the way up to about 5. So this is CR going from 0 to, you can go up to 5 times in this case. And the other things that we talked about yesterday is the wind pressures. So okay, so here you see this is the figure giving you the peak incident pressure versus the peak dynamic pressure. Okay, so this is the peak dynamic pressure, this is the peak incident pressure, the density of the air behind the shock front. So there are 3 different things. So if you see the peak dynamic pressure and the particle velocity, so this is a curve that gives you the velocity, particle velocity, and this is the dynamic pressure. in psi. This is in terms of the incident pressure. So, reflected pressures will be 5 times. Our design is for reflected pressures. So, when you are doing some calculations, this may be a good checkpoint for you. We'll go through tomorrow an example of how to calculate loads on walls of a structure. So, in that example, when you want to do some checks, to this curve may be a good way to check what you have. So, just to get some numbers again, we are looking at, this is PSO, and again up to 100, it's almost a linear variation, but this is in the logarithmic scale, so keep in mind that's a logarithmic linear approximate variation. So, your dynamic pressures in terms are twice roughly. So, this is approximately dynamic pressure, not twice in the log scale, this is 2 into in the log scale PSO. So, so that gives one more thing, and maybe we can take a break, or if you see how complex it can get for vented type, this is, let me paste it. So, this is, if you see, this is the reflected pressure. No, this is not for vented. So, the other thing also we talked about was the structure, and you have your explosive, and here you have R, and then you have at this point, for example, you have pressures. So, this is, let us say, P1 and this is P2. This is reflected, and this is your angle of incidence alpha, let us say. So, you see all the different curves, it is not only dependent. So, this is CR, which is PR alpha divided by PSO. This is in terms of PSO. PSO is right here. So, it not only depends on the angle of incidence going down, but it also depends on the peak incident over pressure value. Many relationships you will see, even the duration, a lot of things are based out of PSO, and and how do they come up with these kinds of curves with these jumps. A lot of it is again shock physics. Those are the experts who come up with. A lot of this research was again done during times where we did not have all these computers, numerical techniques. So, in my time, I don't know, I like to say this, so I might as well say, we just transitioned from slide rules to log books. I don't know if you've used log books, log tables for calculations. I mean, that was the biggest fear when I took these exams at IIT BTech was, do I know which log table and how do I get to it quickly within the 1 hour exam time? So, we used to memorize log tables so that we can multiply quickly and solve the problems that our professors, tough professors used to give. So, took a lot of good training out here. So, these were developed even before those times, right. So, analytical expressions derived from first principles calculus and differential equations, and those were big. That development is actually now stunted in many ways. You won't see a whole lot of analytical expressions coming in the fast, right. Am I that a fair statement?
Still KB equation, Kingari-Bonmash equation is what is?
Yeah, we'll talk about that too. So you'll see that, and we'll give you roughly an age for that. So that is the trade-off from now to when I started, or you'll see. But value is we still use them even now. It's hard to do any numerical studies or experimental studies and come up with analytical expressions or that can be used in an effective manner.